All right, we're back. So we'll continue our discussion. All right. So now we have identified a class of problems called NPC problems. These are hardest problems inside NP. So usually we say these problems are intractable problems. So quite often you see these are called intractable. All right. So that's what we have. Now, a couple of comments about problem inside. Of course, as we mentioned, that if any problem inside the NPC can be solved in polynomial time, then all problem inside NP can be solved in polynomial time. It does not look to be likely, so we have a very strong evidence that indeed an NP complete problem are very difficult, and they are not likely to be solved in polynomial time. All right. Second thing is the notion of polynomial equivalence. So we say that two problems are polynomially equivalent. If they can reduce from one another. So that we can reduce pi to pi prime and reduce pi prime to pi. So meaning is if one of them can be solved in polynomial time, then the other one can. So that's why we say they're polynomially equivalent. So we can either solve both problems in polynomial time, or we can solve neither in polynomial time. All right. So then all problems inside NPC are polynomially equivalent. Or maybe I just say all NP complete problems. It's easier to say that way. All right. So have a good picture about this class NP and NP complete problems. For those who have taken the formal language course, do you have a better understanding of these notions now? I hope you do get a better picture of the class of what we mean by NP complete problems. All right. Okay. Now the big question is, do we really have an NP complete problem at all? Because you see the definition of NP completeness, NP complete problem very, very demanding. So it has a property that every problem can be reduced to this problem. It's very, very, very demanding. So it may be the case we don't have such problem at all because so demanding. It seems not likely actually. How can we reduce every problem to a single problem? And these problems are really of different nature. Some dealing with graphs, some dealing with Boolean formulas, some dealing with scheduling, some dealing with linear programming. All of them have different natures. How is it possible that we can reduce thousands of different problems, actually in theory, infinitely many problems to a single problem in polynomial time? Intuitively, it does not seem to be possible at all. Surprisingly, we indeed have NP-complete problems. So inside, indeed, it exists at least one. So indeed, we have some problem inside. So of course, it's difficult to identify a seed problem inside. So one that was first identified as a problem inside NP is called the satisfiability problem. So that's a famous Cook theorem. So that's the first problem that has been proved to be NP-complete. Now sit back and think about this statement. Actually, it's very surprising and amazing, because in order to prove that a problem is NP-complete, we have to reduce every problem inside NP to this particular problem set. I will define this problem in a minute. All right. So how is it possible? Actually, we even don't know what problem, the solid problem inside NP. Actually, we don't know. We know, by definition, we know what a problem is in NP. It has a polynomial time verification algorithm. But in terms of individual problems, there are infinitely many of them. So how can we reduce infinitely many problems into a single problem, even without knowing these infinitely many problems? Actually, we don't know these problems. Theoretically, we know the problem is in NP, but we don't know the solid specification of the problem at all. So it's really surprising. Actually, it can be proven in that way. All right. So the reason actually is because of this NP. So word NP. Anyone thought about why we use word NP for this class? Does it stand for no polynomial time? Actually, it's not, because it means polynomial time verification algorithm. It does not stand for no poly time, because P also inside NP. Yeah, when you said non-deterministic, then you knew something about Turing machine. Okay, so actually that stands for non-deterministic. So NP stands for non-deterministic polynomial time. All right, so that has something to do with non-deterministic Turing machine or non-deterministic algorithm. I'm not going to get into details. Anyway, NP is equivalent to say that a problem admits a non-deterministic polynomial time algorithm. So this class is same as saying that the problem can be solved in non-deterministic polynomial time. So that means there exists non-deterministic Turing machines that solve the problem in polynomial time. All right, I'm not going to get into too much details on this one, because you may even get confused if you're not familiar with non-deterministic Turing machine or non-deterministic algorithm. Anyway, so you can think about verification algorithm, but in order to prove that this particular problem is NP-complete, actually Steve Cook used this characterization of NP problems, all problems inside NP. So use this characterization. So use this characterization that every problem inside NP can be solved by a non-deterministic Turing machine in polynomial time. Then the behavior of this non-deterministic Turing machine can be encoded by set. So that's the main idea behind the Turing Steve Cook's proof. So what he did actually is to describe the behavior of a Turing machine, non-deterministic Turing machine, by a formula, Boolean formula. Therefore, reduce the problem into the satisfiability problem of Boolean formulas. That's the main idea behind the proof. The proof is complicated, but it's actually not that complicated. A few pages. I still remember the basic idea about this proof. I perhaps can work out the detail in a day or so. Okay. I think when I was undergraduate student, I think in class, I'm not 100% sure, but perhaps I learned it when I was undergraduate student. Of course, I don't really understand it. I understand the proof only after I got my PhD degree. One day I had nothing to do, I read the book. Then I spent a day or half a day, I forgot. But after that, I fully understand the proof. So that's why I say, if you give me a day or half a day, I can reproduce the proof. Because now I think I really understand as a proof. All right. But of course, I'm not going to discuss it in class. It takes at least 1 hour. No, 1 hour maybe not enough. 2 hours perhaps. All right. But anyway, Steve Cook indeed come up with the first seed problem. This one was also independently proven by Russian theoretician Levin in 2 years later. All right. Okay. Yeah. Actually, I really learned a lot from Steve Cook because I graduated from University of Toronto, and he was a professor over there. And one thing I learned from him is actually what I will put in the final exam is for a problem, if you just say I don't know, I give you 20% of the mark. That's what I learned from Steve Cook. The reason is I think he told me that it's better that you know that you don't know. That shows you at least know something, right? Make sense? So I really like this idea. And in final exam, I think for some problem, I will use his idea that for some problem, if you just say, I don't know, I will give you 20%. So now you think about it, it's a simple idea, but look, it's from Steve Cook. Okay. All right. So I really learned a lot from him when I was in Toronto. When I taught algorithm course, I noticed that how he designed these questions and how he designed these marks. So I asked him. That's what he told me. So I have been using that for many years in this department, like give 20%. All right. Okay. But anyway, going back to our theory of NP completeness. Yeah, long answer, of course, get no mark. Okay. Okay. So now let's define what this problem is, satisfiability problem. So in short, it's called a set. So it's a shorthand for satisfiability problem. So in short, we just use SAT. All right. So this problem dealing with the satisfiability of Boolean formulas. As input, we have a Boolean formula. But in special form, in conjunctive normal form. So let me put F here. All right, so the problem is we have a conjunctive normal form. Sorry, conjunctive normal form, sorry. All right, so here is an example. We have Boolean formula in conjunctive normal form. Maybe U1 or U2 bar or U3. Yeah, the pen does not work very well. That's conjunctive normal form. It's conjunction of disjunctions. So here FU1 bar maybe or U3, maybe U3 bar. So here is maybe U2 or U3 or U4 or U5, maybe, sorry. And maybe one more, U1 bar or U2 or U3 or U5 bar. All right. So we're dealing of a certifiability of Boolean formulas. So what we need to do is find the choose assignment for Boolean variables. So choose assignment, this one is for Boolean variables. So each will get a value. So you give a choose assignment. So U1, U2, U3, U4, U5. So maybe 1, 1, 0, 1, 0. So whether exists such a choose assignment that will satisfy the Boolean formula. So that's a certifiability problem. But often we do not use this form. Rather, we use the following form. In the definition of certifiability, usually we use this in the following form. You will see that in most paper or literatures, set is defined in this way. Typically, it's defined in this way. All right. So what it means is this. So we have a set of Boolean variables, U, such as, so 5 variables, so U1, U2, U3, U4, U5. Now, clause. A clause is just a disjunction of literals. So each variable, Boolean variable, it has 2 literals. So UI, it has UI itself or its negation. So these 2 are called the literals. So these 2 are called the literals. Okay. And a clause is just a collection of literals. Clause is a collection of literals. Such as we have U1, U2 bar, U3. That's a clause. Meaning is actually corresponding to U1 or U2 or U3. It's a shorthand for Boolean formula. A clause is a shorthand for disjunction of a collection of literals. All right. So this collection of clauses So it's exactly corresponding to the Boolean formula. The Boolean formula will C1 and C2 and say Cn. So each CI is a clause. So that's the same thing actually, but we just use different form to represent the problem. Typically, we define it in terms of collection of clauses. Collection of clauses. Sorry, I missed the S here. All right. So that's the definition of a satisfiability problem. So is that clear? The definition? A very special case of satisfiability problem is called a three-set. A three-set. Three-set is a special case of set. Where each clause contains exactly three different literals. All right, that's three set. And later on, we'll see that very often it's much more useful than general satisfiability problem. In order to prove that a problem is NP-complete, a three-set problem is much more useful. So that's why we need this special case. Even if they're not different, they're still different. Yeah, it's actually exact definition. It's better to be different. Sometimes you need them to be different. So in general, of course, it's a container case that even they are not different, it's still difficult. But it's better that it will be easier in proof if all these three literals are different. For technical reasons, it's better that they are different. You will see, okay? Otherwise, if for some proof, it's not good enough. All right. So that's the idea of a satisfiability problem and three sets. So three sets typically each clause will have will of this form. Just as a two set. That's three sets. We have seen two sets. Then each clause has exactly two literals. That's a two set. So that's three set. All right. So Steve Cook proved that satisfiability problem is NP-complete. So now we do have C problem. Oh, by the way, Steve Cook received Turing Award because of his work for theory of NP-completeness. So that's like a Nobel Prize in computer science. All right. So now we have first problem that is NP-complete. So now how can we prove that a problem is NP-complete? So one way is we can do like what Steve Cook did, like Cook did. So prove that every problem reduces to your problem. So if you we want to prove pi is NP-complete, how can we do it? So of course, first thing is we need to prove pi is inside NP. All right. Okay, I will make comments a minute later about your observation. Okay. Second, we can use the idea of Steve Cook, reduce every problem inside NP to our problem. So we can do it in two steps. Of course, first step, don't forget this one. typically it's just trivial. For most of the problem, you can say it's trivial, that's the problem belongs to NP. So typically you will see that it's obvious. In the proof, typically you will see that it's obvious. In an NP completeness proof, typically you will see this. It is true. It is most often 99.9% of time, maybe at least 99, maybe 90% of time, it is trivial. So you can say it, but don't forget to say it if you want to prove that problem is NP complete. All right. But second step is almost impossible because look, a cook received the Turing Award by proving three sets as a satisfiability problem is NP complete by doing things in this way. Now, if you want to prove that your problem is NP complete, if you want to reduce every problem inside NP to your problem, I'm not sure you will get Turing Award too, but at least you will be very famous if you're able to do this. If you were able to do this directly. For example, if you can prove that the vertex cover problem is NP complete. If you can reduce every problem directly to vertex cover, people will certainly be amazed, at least will be impressed. So it's almost impossible. It will be too complicated, too difficult to do things in this way. All right. Now to make it practical, we need a very important property of polynomial reduction. So before that, let me make a comment about your comment, Chen your comments. Okay. So you said reduce to 3 set, or reduce to some other problem that reduces to 3 set. Okay. So what you are doing is in order to prove that pi prime is NP complete, you want to prove that pi is NP complete. You reduce pi to 3 set. That's same as saying that in order to prove that you are famous, in order to prove that you are famous, what you are doing, you say, do you see? That's a very, very common mistake you may make when you try to prove that a problem is NP complete. It's a long way of reduction, totally wrong. Correct way is to reduce from 3 set to the problem pi, or to other NP complete problem, to this problem. Okay, so that's a very common mistake when you try to prove that a problem is difficult. Don't reduce your problem to a difficult problem. To prove that a problem is difficult, you need to reduce a difficult problem to your problem. That's a common mistake. It's very good, actually, you put that comment, because that's a very, very common mistake. All right, okay? Now you're famous. All the classmates will remember you. Okay, that shows you are famous. Now all your classmates, at least a student who attended the class today, knows you. So that proves that you are famous. All right, okay. All right, now going back to this, because this, as I said, this one is very difficult. So what do we do? Let's say a very important property of polynomial reduction called transitivity. This polynomial reduction, or this one, is transitive. So that means if I can reduce pi 1 to pi 2, and I can also reduce pi, and I can reduce pi 2 to pi 3. So that implies I can reduce pi 1 to pi 3. That's the transitivity. That's also the importance of we use polynomial time in the reduction, because polynomial is transitive. composition of polynomial is still a polynomial. Some other function may not have this property. Linear function, quadratic function, for example. You combine composition of quadratic function maybe to n to the power fourth. All right, so that's very important. Because this transitivity, that will enable us to reduce step 2 this step 2. Now we can, instead of using this one, we do the following. So replace it by 2 steps. Okay, so instead doing reduction from all NP problems, you choose a single problem, NP complete problem. Give a reduction from this NP complete problem to your problem. So that's because transitivity of polynomial reduction, we can do this. All right, so what happens is sorry. Let me also erase this one. Yes, that's the last available page I can use. It's up to 12 pages, but I have to erase something in order to. Now, so this, we identify a problem pi prime here. Make a reduction from this problem to your problem pi. Now, by the transitivity, so we know every problem can be reduced to pi prime. So transitivity implies that all these problems can be reduced to your problem. So that picture illustrates why this one works, because of transitivity of polynomial reduction. All right. Now, this one, actually, it's not that easy. Choose the right problem is not easy, but the experience helps a lot. This one is not easy step, actually. Choose the right problem. But of course, for us, now it's trivial because we only have a single problem available. For the time being, it's single problem available. We only have set available. So in order to prove that our problem is NP complete, the only thing we can do is reduce satisfiability problem to our problem. But once we have more problems, it's getting more and difficult to choose the right problem, because there are thousands of known NP complete problems. So choose the right one is really not easy at all. Okay. Okay, so this is the third step is a key step. It's difficult and it's really varies. Some of them are really simple, some of them very difficult. Really depends. So here you really need to understand the problem and need to do a lot of reduction in order to really understand, really know how to do reduction. So that's again, practice is very important. This is not easy at all. Myself, maybe I've done at least maybe 50 reductions and have seen maybe 100, at least 100 or 200, I don't know, I can't remember, at least 100 different reductions. So for me, I have a very good feeling about NP completeness. Normally, I have a very good feeling. Give me a problem. My brain naturally works, will tell me whether it's likely to be NP complete or not. Sometimes very fast, in seconds. A few days ago, when I was walking up, perhaps last Monday, I was thinking about whether I will have time to talk about reductions. So I was thinking a problem. It's related to minimum spanning tree. Find the key verses. A minimum spanning tree on a subgraph with key verses. So for that one, I immediately, within seconds, I know that if I want to prove that one is NP complete, I will use a reduction from standard tree. Okay. So you really need a lot of practice in order to master this part. It's not easy at all. So you really need to do a lot of practice. All right. Okay. So let me summarize this part. Let's see. Is there one page left or something? Okay. So a couple of things. Yeah. Before I forget, anti-heart. Okay. Step 2 and 3 actually that shows that the problem is anti-heart. So that really shows that pi is anti-heart. All right. So in order to prove that the problem is NP-complete, what you do is do two things. One is pi belong to NP. That's the easy part, typically trivial. Then the hard part is show pi belong to NPC. So normally this one is done by a reduction from an NP-complete problem, or actually NP-hard problem will do it as well, NP-hard problem. Every NP-complete problem is NP-hard, all right? So that's normally how we do it. Now, a comment, strictly speaking, when we say that a problem is NP-hard, that's only also referred to all decision problems. All right. So strictly speaking, when we say that a problem is NP-hard, this problem is also a decision problem. But as a convention in practice, quite often we will abuse NP-hardness. Usually we don't abuse NP-completeness. So if a problem is NP-complete, say vertex cover is NP-complete. Very often we will say that it's related to search version and optimization version. For these two versions, very often we'll say they are NP-hard. So these problems are not really, they are not decision problems. They very often will abuse the notations and say search version, decision version. So actually find the vertex cover to minimize size, or then we say this problem is NP-hard. But typically we don't say that these two versions are NP-complete. All right. So as a theoretician, you have to distinguish these two different things. But as a practitioner, that's good enough. If you can distinct NPC and the NP hardness in this way. So if a problem is NP hard, then you know that then you can say it's search version and optimization version are NP hard. That's good enough. All right. Okay. What else do I need to say before I forget anything? Okay, I think that's it for general framework. Any questions before we go further? Actually, we don't have time to go further. All right, I think I have to delay to Thursday to give you the first proof that other problems are NP-hard or NP-complete. I think I should call it off for today. We'll talk about something about a final exam. Perhaps you are more interested in final exam than the technical things. So on starting from Thursday, we'll get our hand dirty. Okay, we'll really talk about reductions to prove that certain problems are difficult. All right. Okay, I think I better stop here about NP completeness. We'll tell you something about final exam. You have about 5 minutes. Good enough. Okay, let me find the empty one. Okay. So let me tell you something about the final exam. When I started to design final exam papers, I found it's quite difficult for me this time. The reason is because we have face-to-face exam and also have online exam. So these two, of course, they are not exactly the same. It's difficult to control online exam, more difficult, I think. Yeah, definitely. It's more than MP hard, I think, right? So then the first thing come to my mind is whether I should make it closed book exam or open book exam. Actually, an ideal one actually is an exam with maybe a few pieces of cheat sheet. A cheat sheet will force you to review course materials. But again, as I said, it's difficult to control for online exam. So finally, I think I will use open book. But perhaps that will be limited to paper material only. Because it's hard to imagine that you will bring a computer to the exam site when you have face-to-face exam. So most likely it will be something like open book. You can have all paper materials. If you want to bring books, it's all right. But it will limit it to open book, just paper materials. But the problem is open book exam is usually more difficult than closed book exam. Yeah, online exam, you need to turn on cameras. Yeah. All right, so typically it's more difficult than closed book exam. But because of two different exams, I think open book may be fair, more fair, because otherwise online one will be have more advantage. All right, so I think we'll use open book exam. But the problem is I cannot give a very easy answer question like a definition of NP completeness. That's trivial, right? That's too easy. All right, but anyway, what I'm going to tell you is we'll tell you some problems that most likely these will be in final exams. So you can, if you just want to pass the course, it's almost good enough if you know how to do these problems. Okay, so I give you something here. So let's do it in reverse order. So as I said, is cover up to theory of NP completeness. So for this one, you must remember reduction from 3 set to vertex cover. So for this part, you must remember this reduction. This reduction will be in the final exam. Of course, may not be exact form, otherwise too easy. All right. If closed book, usually the question I give is give you an instance of 3 set. You give me a construction, you give me the instance of corresponding vertex cover. In closed book exam, typically that's what I will give. But for open books, it may be something more than that one, otherwise trivial. All right. But this one will be in final exam. So that's for 3 set. Then in terms of algorithms, we have dynamic programming. We have grid method. We have divide and conquer, systematic search. So if we just focus on these 5 things, I think if you have really fully understand these 5 things, you will certainly pass the course. So for each, I will give you 1 or 2 problems that you must understand. All right. For dynamic programming, I think subset problem. A subset sum problem. Of course, problem related to it, a knapsack. All right, for grid methods, such as minimum spanning tree. Yeah, the pen suddenly does not. Minimum spanning tree. All right, for divide conquer, perhaps merge sort, multiplication, integer multiplication. I locked the browsing because it's not that easy. Okay. Yeah, I really don't know what lockdown, how to do that one. I'm basically a math professor, a theoretical professor. Okay. Yeah, of course we can do that, but again, online is difficult to control. Some people maybe have many computers. You never know. So okay. So I think it's better to use open book to be fair to students who taking face-to-face exam. All right. Also, the problem may not be exactly the same. The problem may not be even exactly the same. Okay, in order to control that, systematic search, then BFS and DFS. I think that's good enough. If you just want to pass a course, if you fully understand these things, that should be good enough. I mean, fully understand these things. Not just on the surface. You really need to understand the principle, the idea behind these things. All right. If you fully understand these things, that will ensure pass, I believe. Normally, when I design problems, I don't know why, but I really usually have a very good feeling about the average marks you will get. Normally within five marks, 5% actually, 5 marks or 5%, maybe 5 marks, not 5%, maybe. Sometimes even as close as one mark. 2 years ago, I think 2 years ago, for algorithm course, my expected average is 65, eventually 64 or something. I had no idea. I was surprised when I see when result came out. And last term for discrete math, I think, middle term, actually, the initial mark is lower than I expected. I want a little bit, so it's a 5% lower or something. But then eventually, the reason is the reason actually is TA made a mistake. After correction of that mistake, it's only 2% in my close to my expected average. So I think I have I don't know why, but I do have a very good feeling. So I may change the face-to-face exam questions, maybe to fit for the online version. It's possible. All right. Okay, so that's what I can tell you about the final exam. So I certainly cannot tell you exact problems that will be in the final exam. Okay. I will give you two exam paper from previous years, so you can take a look of the questions. All previous year exams are closed book. Last 2 years ago, the actual exams are multi-choices, but that certainly will not work for online. For face-to-face, it's okay. Multi-choice, it's more objective in a sense, but for online, it will not be good. All right. Okay, I think that's it. So we'll see you on Thursday. We'll get our hands dirty. And TA, I believe they will send you homework marks for homework 2 and 3. And I will post homework 4 this before this Thursday. The last homework will be posted this Thursday. All right. Yeah, multiple choice question, just A, B, C, D. Yeah, that's multi choice. Multiple choice. Sorry, multiple choice. Sorry. Yeah, multiple choice. Yeah. Okay. All right. Any questions? No, you don't have a choice. Otherwise, how you can we can control that? We cannot control that. Okay, you cannot opt for open book exam or closed book exam. No, no, you can't. Okay, it will be open book. All right. Okay, so see you on Thursday. Bye bye.